Hello everyone. Welcome to our number 13 lecture. Today I'm going to talk about the second example on the topic of control volume, mass and energy in control volume systems. And in the beginning, I would like to go to our blackboard to check the example that we're going to solve today. So if we go to lecture materials, lecture examples, number 4, and here is the second example that I'm going to solve for you in this lecture. Please, as always, keep this in front of you because I'm going to refer to some information. So in the beginning, like to all our lectures, I'm going to read the whole story for you, and we are gonna um hold on a second, please. Okay, and we're gonna imagine what is happening in our story, in our um, question. So the question number 2 says that a zero point 0.3 meters cube rigid tank initially contains refrigerant 134A at 14 degrees C. At this state, 55% of the mass is in the vapor phase and the rest is in the liquid phase. The tank is connected by a valve to a supply line where refrigerant at 1.4 megapascal and 100 degrees C flows steadily. Now the valve is opened slightly and the refrigerant is allowed to enter the tank. When the pressure in the tank reaches to 1 megapascal, the entire refrigerant in the tank exists in the vapor phase only. At this point, the valve is closed. Determine the final pressure in the tank, the mass of refrigerant that has entered the tank, and the heat transfer between the system and the surrounding. And we have the answers at the end. Great. So in this example, if we pay attention before we do anything, we can see that we have some sort of like a transient or temporary flow rate that is coming into our system if we define the tank as our system. So let's do it this way. So we define a tank as a system, and then we have a constant flow rate which is totally separate before we open the valve. Then after we open the valve slightly, we have a temporary flow coming into the tank. After certain amount of time, then we close the valve, right? And nothing is mentioned about the time duration, so we don't know how long it takes, right? But we know that it's like kind of a temporary process, and it makes this question slightly different comparing to the previous one that we solved before, which was about, let me show you here, which was about a heat exchanger that we had a constant flow rate and it was going on forever basically. They didn't mention about like a valve open or close or like something is coming in and then we limit that, we stop it, or no. It was just a flow. Constantly operating. Okay. But in this example, in the second one, we have a temporary um, condition that makes it a little bit different than the previous one, and I'm gonna mention that later in the lecture. Okay. So as always, we need to define our system. There are some certain steps that we need to take before we start solving the example. So the first one is, what is our system? Or in the other words, what are we interested in? We're interested in the condition in the tank. So I define the tank, the walls, the opening, the valve. I mean like this the content inside the tank as my system, right? And then I need to have a summary of the questions that are asked, which are T2, that I define T2 as the final temperature in the tank, and also it asks for the mass which entered the tank meanwhile that the valve was open. So let's say the refrigerant into the tank through the valve. And also it asks for the heat that transferred to the system. If you pay attention to the text, the sentence, it says the heat at part C, it says the heat transfer between the system and the surroundings. So it remains the question as like kind of like vague way that it doesn't mention anything about the direction of the heat transfer. Either it might be from the system to the surrounding, so the heat is leaving the system, or the system might absorb the heat from the surrounding. So, but here in the text it doesn't mention anything about the direction. So we need to assume that like it's like coming in or coming out. Then according to the sign, the sign of that number, we can tell that it was coming in or outlet. Anyway, so I will talk about it later. And so I just define it like Q in. I assume that the heat is going into the system. If I got a negative value, it means, ooh, my assumption was wrong. So heat is going out of the system. So I will stay with Q coming in. This is an assumption. The heat I assumed the direction. I assumed that heat is going into the system. Let's see um, what would I get? What sign am I gonna get? Anyway, so after we define our system as the contents of the tank, then we need to draw it, right? We need to draw the schematic of our system. So let's say the tank is like underneath the pipe, the supply line. So, and it has like real walls. It's like made of like, I don't know, stainless steel or like something. And then the valve is on top of the tank and it connects the tank to the pipeline. So the upper boundary is gonna be open boundary, right? Because I have an opening here. I have a valve. So I would draw that as a dashed line, which represents some sort of imaginary boundary because it's open to the supply line. Meanwhile, that the valve was open. Anyway, so these um, what is it called? Like solid lines are real boundaries, which are like tank walls. Tank walls. Okay, and the dashed line is imaginary boundaries. Okay, awesome. Why why is it imaginary? Because the valve. Hi again. I'm sorry about this. Something went wrong with my surface. I need to check that. Okay, so let's go back to our solution. So here, I was talking about these imaginary boundaries that I've defined this because the valve connects because the valve oh sorry okay because the valve connect is connected to the line because the no cause sorry let's say it this way because is connected to the supply line for certain amount of time, which is like when the valve is open. And here is the content is my system. And also I assumed up there here that Q goes in. So I have the Q in transferring to the system by, I mean, like through the real boundaries. And also, since I have the inlet here, like an actual inlet that like the mass can transfer into our system, so then I would have m dot inlet, right? Or let's say, because it's like a temporary flow, I will call that m, just a specific amount of mass entered the system, and it carried energy with itself. E inlet, right? So the mass, let's say the valve was open for an hour, so like 5 kilogram of the refrigerant came into the system, and it carried like 100 kilojoule with itself to our system, right? So that's like simple. And then let's go to the definitions. I mean, no, before the definitions, let's talk about our famous summary table. So we can define 2 points in this example. Point one, which is the initial state, when like the refrigerant is at 14 degrees C. Then we open the valve, a process is going on, and then we close it. Now it's point two, which is the final state. So just these 2 points would be enough. So I will call point one as the initial state and point two as the final state. I'm a little bit worried about this software, if it's going on right. Yeah, apparently it's working. Okay, now let's have the summary. It says that so it's a rigid tank, which means that volume is constant. It's solid. The volume doesn't work. The tank walls don't work. So the initial volume is zero point 0.3 meters cube, and it's gonna remain constant through our process. Therefore, I'm gonna have same volumes. And then it says that the temperature is 14 degrees C initially. 14 degrees C. At this state, 55% of mass is in the vapor phase. If you check, I'll tell you. So, as we defined before, a mixture quality is defined as X equals M sub vapor divided by total mass, right? You can double check that on pages 12 and 13 in lecture note number 6. Okay, great. So here it says that 55% of the mass is in the vapor phase. So 55 um like of the whole thing. So like 55 divided by 100 here is 55 vapor and 100 total. Anyway, so it means that x1 equals 55%, which is 0.55. Okay, great. And what else do we know? We know the condition of the refrigerant that is coming into our system. I'm not going to talk about it now. And also I know that at the end, P2, the final pressure is 1 megapascal, because it says we will close the valve when the pressure reaches to 1 megapascal. And also it adds that at this point, the entire refrigerant in the tank exists in the vapor phase only. So that would be a saturated vapor, right? Because in the beginning we have a mixture of, see, X1 is 55%. It means like a little bit more than half of the mass is vapor, and the rest of it, which is 45%, is in mass phase. So basically, we're like adding the hot refrigerant into our system, which is like 100 degrees C. You can see that it takes us 1.4 megapascal at 100 degrees C. So basically, we're warming up our system. And then this mixture uh, is like it reforms to like some sort of, it goes toward reaching to the saturated vapor, right? It's a mixture, so you warm it up, it evaporates, the liquid evaporates, and as soon as it gets to the vapor, only like the whole mass is vapor, we close the valve. That point would be saturated vapor. So X2 would be 1 because the whole mass is vapor now. The first question was T2, right? So let's find it. T2. How much are you? T2. Okay. Let's go. Let's check our summary table. We have pressure, and we know that the whole mass is vapor, and it's saturated because as soon as it got to this phase, vapor only, we close the valve. So it means like right at the saturated vapor, we stopped it. We didn't go to superheated. We didn't go further. We didn't add heat furthermore. We just stopped at the saturated vapor phase. Therefore, these information are enough, right? I can find the exact point on the table. So at point 2, which is the final state, the material is, once again, please pay attention to this part. You need to write the material. You need to clearly specify for yourself that what is the material, because then you need to go to the table, to the corresponding table, and then you might get confused and like the material is like R134A and you go to water table and everything would be wrong, Please, please, it's frustrating, but please write it. Just make it clear in front of your eyes. Once again, one more time. The material is R134A. Okay. And as I told you before, it's saturated vapor because we closed the valve as soon as we got the whole mass as or in vapor phase. So it's saturated vapor, right? In the table here we have A1, the table A11 here, A11, which is about, oh my god, I have A11, which is the saturated um, properties or like values at different temperatures, and then in the next table I have same information at different pressures, right? So here I have, what do I have? At point 2 I have pressure, so I need to use this table, which is A12, and the pressure is 1 megapascal. Therefore here is the line that I'm looking for, because at point 2 I know that pressure is 1 megapascal, 1000 kilopascal. What am I looking for? I'm looking for temperature. I'm looking for saturated temperature, which is here, 39.34. So where is, okay, here. Therefore, according to table, there you go, table A12, okay, T2 would be T saturated at 1 megapascal. Once again, why am I choosing the saturated temperature? because in the phase change process, when we kind of like evaporate the liquid, like yeah, evaporate the liquid, and the material transforms from liquid phase to vapor phase, temperature and pressure would be constant, right? And they would be both at those values in the table. See, like 1 mega, for example, 1 megapascal, for example. Oh my God. For example, here 1 megapascal and 39.34. These two numbers will be constant all along phase um, phase change process. Therefore, T2 is 39.37 degrees C. Okay, here is the answer. And I need to update my table, my summary table, with the red color. T2 is, I just got it, 39.37 degrees C. I might need this in future, so I will add it to my summary table. The next question is, how much of mass would be entered to our system meanwhile that the valve is open? Okay, so it's just a simple question that how much mass entered the system, m inlet, and the unit would be just kilogram, simply like 3 kilogram. 3 kilogram went into the system. This is the second question. In this case, to find this mass inlet, we have two ways. We can take two procedures. The first one is, well, we can assume that we have some sort of flow rate like m dot, and it took 1 hour, so we can multiply the time duration by the mass flow rate to find m. So all we need to do is just find mass flow rate, multiply that by time, you got the mass, right? So the first one is multiply mass flow rate entering the tank by time duration, right? This is one way. But there is a problem. We cannot, because if you look at the text again, you look at the example, it does not mention anything about the time. It doesn't say like it took an hour, 1 minute, 5 minutes. We do not know how long it took, right? So this is not the way. We cannot choose this one. The other way that we can choose is just as I told you before, I have picked the initial and final states as point 1 and point 2. Initial is before I open the valve, and final is like after that mass entered the system and I close the valve. So uh, if I will be able to solve for initial and final masses, that how much of mass is in the tank before I open the valve and how much of mass is in the tank after I close the valve, then if I subtract these two guys, I can solve for how much mass entered the tank, right? It's simple. So I can define like m inlet equals the final mass minus the initial mass, right? And just forget totally about the flow rate and like m dot per time. Just forget that. So we're like somehow switching between an open system which deals with like flow rates and stuff to a closed system which has just initial and final state. You see, it's like here is like tricky because I have an open boundary here, the dash line, but I'm like kind of switching to the closed system. I'm defining a final and initial and final state, so it's a little bit, it might be confusing, but it's just Think about it simply. Before I open the valve, after I open the valve, close the valve. That's it. Initial, final. And forget the flow like m dot and stuff. Just forget all those things, all those equations, everything, all the parameters had like little dot on top. Just forget all those things, right? And but now I'm defining two new parameters, M1 and M2, that have no idea about those. But still, I'm happy. I'm happy with these assumptions because at least I can do something, right? So once again, let's check our summary table. Okay, now I'm thinking about the initial and final mass. At point 1 and point 2 both, I have the volumes, point 0.3 meters cube, point 0.3 meters cube. Okay, that's good. And at point 1, I have temperature and the quantity. So it's enough to find the specific volume, the little v. I can find it, I can look it up on the table and solve for v1, the little v1. And likewise at point 2, because again, I know it's saturated vapor. So I know how much is the specific volume. That's going to be just Vg on the table. It's like the specific volume at saturated vapor. So I can solve for little v's, the specific volumes at initial and final states. And I know that m equals capital V divided by little v, volume divided by specific volume. Then, wow, it's hopeful. I'm hopeful now because now I can solve for m easily, right? So let me put a note here for you that we have initial and final states, right? I mean, V1 and V2. It's capital V, yes. And I know that M equals capital V divided by little v. So we need to be able to solve for M. I need to solve for little v first, then put it in this equation, and then get the mass. So I need to find specific volumes. Specific volumes, right? Little v1 and little v2. Okay, let's go for these guys. So based on our summary table, at point 1, which is my initial state, one more time, I know that the material is R134A, and I know that X1 is 0.55, which means that that is a liquid vapor mixture. 55% of the mass is in vapor phase and 45% of the mass is in liquid phase. And I can solve for V1 as like this way, like VF plus X1 VFG. If you check these slides again, these notes 12 and 13, then you'll see what I'm talking about. Anyway, so what is my temperature? Tell me, it's 14 degrees C. It's 14 degrees C. So this table doesn't work because it's that at different pressures. I need to go to the other table, 811, and where is it? Ooh, I don't know why. Because oh my god, oh my god. Da, 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 da. Oh, there you go. That's enough. Even no, that is enough. The first. Oh, oh no. Oh no. One more. One more. Okay. So this is 8020 is VF, and 434 this is VG at that temperature. And this is exactly what I'm looking for. Exactly what I'm looking for. So check this out. So VF at 14 degrees C was 0.000, okay, 18 meters cube per kilogram, and Vg at 14 degrees C was 0434. Same unit. Just plug it in, put it in that equation here. Therefore, V1 is okay. So little v1 is 02427 meters cube per kilogram. Now let's solve for v2 at point 2. Come on. Okay, at point 2. You can like simultaneously solve it. You can go to tables and just check like meanwhile that I'm writing all these. Yeah, 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 why not? Because it takes time and I'm just writing some information. So material is R1. I'm emphasizing on rewriting the material because you need that to make sure you are going to the right and correct table. At this point, I have a saturated vapor, which means x2 is 1. Then I need, did I write the table here? No. A11. Here, because I have the pressure, I need to go to the other table, to the next table, which is A12. Okay. And it's saturated vapor. So it means that V2 is Vg, right? It's saturated vapor. Look it up. See? Saturated vapor here. Saturated vapor Vg. At 1 megapascal, which is uh-oh. Uh-oh. I made a mistake here. I made a mistake. I forgot to continue writing that. I got too excited with all the symphonies that I'm singing. But the final answer was correct because I'm double checking that with my notes. So, and here it's 020 3, 2, 1, all with the same units. Now I can go to that equation to find m here. Capital V divided by little v. M1 equals V1 divided by V1, which would be 0.3 meters cubed divided by what we just got for little v1. Oh, 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 oh. Let's play with the units a little bit. See, I have m cube, and then this guy goes up. Tum tum goes up. Awesome, 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 awesome. So M inlet, as I've told you before, is this final minus initial, which would be 14.76 minus 12.36. So M inlet would be 2.396 kilogram. That is important because we're gonna need that in future. And let me update my table because I'm gonna need the mass M1 and M2, the mass at the initial and final states in future when I'm solving for heat. So M1 was 12.36 kilogram and M2 was 14.76 kilogram. Give me one more page, please. Okay, good boy. Now the last part, Q in. Okay, so when we talk about the heat, it's kind of clear that we need to use the first law, which is about conservation of energy, right? But if you check, if you check the lecture number 9 and 10, I will write it for you here. You would see that we have two forms of first law. One is in the form of flows and like everything's per time with all those little dots on top of all the parameters like m dot, q dot, w dot, dot 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 dot, dot, right? The other one is like just E or M or U or H, like enthalpy, internal energy, right? And all these parameters are absolute values. It's just energy at that point, internal energy at that state, like mass at that time, right? It's not talking about flow rate. So which one am I supposed to use here? Do you remember that I told you in the beginning that we have, although we have an open system which is connected to the valve, I mean like supply line through the valve, but still it's temporarily, it's open, but it's for limited time. So and therefore we will have two initial and final states. So it's kind of like closed system. Like one, initially it's closed, right? Closed system. Then it's open, but again, it's closed. It's closed system. So I have two closed systems: initial closed system, final closed system. Because at these 2 points, valve is closed, but in between it was open, and that was the process. Anyway, so the first law has two forms. One is steady flow process. For instance, like a turbine or compressor or pump that is like continuously working, 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 working. We have a continuous flow rate forever. Hmm? And we use this form. We use this guy, Q dot in minus W dot in. No, I don't want to write in too much time. Anyway, so Q dot minus W dot plus summation over the total mass carried by, sorry, the total energy carried by mass, all at the inlet, equals Q dot minus W dot plus summation over energy carried by mass at the outlet, everything at the outlet. And just a little note that dE divided by T dt was 0, right? Because of steady state. So this was mentioned in chapter lecture 9, page 13, right? But we have another form. We have another form for unsteady flow rates, or like um, closed systems at initial and final states. So it's unsteady flow process. It means that it is it has flow, but flow was temporarily, right? And this flow created the process in between two initial and final states, two closed systems. I'm sorry, I need to focus. I need to insist on these two, on the difference between these two types of systems, because in next, like in fluid dynamics or thermodynamics, or any other courses related to these topics, you're gonna deal with these different types of systems so many times. So you need to understand it like clearly. So we treat the system as a closed. So we treat or we assume initial and final closed systems, right? And according to first law, we know that the mass coming in minus the mass leaving the system equals the total change in the mass of my system. Therefore, the Q plus all types of work, boundary work, electrical work, friction, like anything, plus the summation over all the energy, the total energy, the enthalpy energy, carried by mass, all through the inlet, minus the same thing through the outlet, equals the change. And the change is in this form, like m2 times e2. Little e is per mass, capital E is just the absolute energy, minus m1 times e1 of my system. Great. And here I define theta as enthalpy plus potential energy plus kinetic energy. Kinetic energy is v squared divided by 2, and potential energy is gz. And little e is u plus, same, pe plus kinetic energy. This guy is for flowing, right? Like turbine, pump, compressor. And this one is for stationary or closed systems, or like at specific points. And please check lecture 10, pages 11, 12, and 13. Give me one more page, please. Okay. Therefore, I'm going to use this guy. I'm going to use this beautiful equation because I don't have any flow rate and I already forgot all those fluorids as I assumed here, as I told you here. See, see. Where is it? Here I said forget the flow and stuff because here we're gonna forget this part. Forget dots. We don't have any information about time, so we need to go for absolute values. W, Q, M, theta, E, and I need to have some assumptions here. First one is potential and kinetic energies are zero or are negligible. Wait, I got confused. Negligible. Sorry. That is zero. And also, no type of work. So the work in and work out are both zero. And we assumed that heat only goes into the system. Therefore, Q out would be zero. And also, one more thing, that we have just one inlet for mass, right? So there's no outlet for the mass. So no mass leaving the system. Sorry. So the summation over m theta out is zero, and it makes it much easier. See, in no work, no work. Q out, not no. This one, no. And here theta, all these guys are zero for theta and little e. Therefore, I'll end up with Q in plus M in H in, because potential, see, theta equals H plus PE plus KE. They're all zero. These two guys are zero, and theta equals H. Everything else is zero on the left side. On the right side, I have M2 E, and E is U, is internal. This is internal energy, which is provided in the tables. So Q in plus this guy equals M2 U2 minus M1 U1. Then Q in would be M2 U little u minus M1 U1 minus M in H in. Previously we found all these masses, right? And this is why I told you, I asked you to add these masses to your table, to your summary table. Okay, I'm gonna finish this. Oh my god. I'm gonna finish this as soon as I can. It's just a couple more lines. Yeah. We are about to finish it. But we do not know U and H. At these 2 points, see, we do not have U. We do not U1. I don't know. U2. I don't know. And also, I do not know the enthalpy of the supply line, which is called H in. This guy. I don't know how much it is, but I know the specific conditions of the refrigerant at that point. So let's find these TUs and the H one by one. At point 1, we knew that temperature is 14 degrees C, and we have a mixture of liquid here. And the material is R134A, and we have a mixture of liquid and vapor with that quality, 55%. So one more time, if we solve the same equation but for internal energy, for U, which would be U1 equals UF plus X1 UFG, then I can find U1, right? So I'll do this here. So at point 1, according to table A11, at temperature here, see here 14 is my temperature. So 14, where's U? Here's U. UF, UFG, and UG. I need UFG and UF here. This guy and this guy. No. Okay. So U1 is UF plus X1 UFG, and T1 is 14 degrees C. So based on what I just showed you, all these informations, and 55% is the quality of the mixture. Is per mass. It's little u, sorry. And at point 2, I know that I have saturated, where is it? Saturated vapor, and I have the pressure, which is 1 megapascal. So I would do the same thing as I did for V, little v, but here for little u. So U2 is U gas at 1 megapascal. So you need to check the next table, A12, and accordingly it's 250.71 kilojoule per mass. So I've got U1, U2, now I need H in. So the condition I'm gonna solve for H in. I know that P in is 1.4 megapascal, and I know that temperature, it's all according to the text, it's given 100 degrees C. Therefore, T, the saturated temperature at 1.4 megapascal equals, let's go to table here. No, this is for temperature. The other one. The next one. Here. No, here. This is the pressure, 1.4 megapascal. It says that temperature is 52.40. So the saturated temperature at that pressure is 52.40 degrees C, which is less than T in, which was 100 degrees C. So it means that this guy is super heated. And it means that I need to go to table A13, which is the table for superheated refrigerant, this one, at that pressure here. Exactly, this is what I'm looking for. So I can find U, and here is like the first column is V, then U, then H, and then entropy S. Here are these numbers. I'm looking for U. I'm looking for H. So this is 330. Now I'm gonna put in all the informations that I got to that main equation here. This guy. As we get closer to the end of the semester and we solve for like more complicated equations, and I mean more complicated questions, then the lectures are kind of like stretching. I'm sorry about that. So here, yeah, they're longer. They're like about an hour to solve one example. But in the exam, it wouldn't be like that. These examples are like comprehensive. So happy we got the Q in. There's just one note that why what was the reason that we were like dealing with internal energy here and here, but we got enthalpy on the other side? It goes back to this equation, which is a simplified form of that equation. And it says that the in so on the left side it talks about the energy coming in or leaving the system. So when you talk about coming in or leaving, you need to include the flow work as well. And the flow work, if you wanna like include that parameter in your procedure, you need to use enthalpy because you're talking about a flow coming in. But if you want to talk about energy of the system at certain states, then you need to talk about internal energy, which is U. So that's why on the left side here, which we were talking about E in and E out, we had theta, which has enthalpy in it. But on the right side, which is here equals these guys, we have the energy itself. And the energy here, we don't have any flow. It's just energy of the system. And internal energy represents that energy. So that's why I had E, and E is defined as U plus these two guys, which are 0. So that's why on the left side, flow side, we had enthalpy, and on the right side, which is stationary side, state side, we had internal energy. Thank you for watching this lecture, and sorry that it was kind of long. Thanks.